Okay, so logarithm rules 2. Properties of logarithms are very similar to the rules for exponents because, as we saw, logarithm is a power logarithm base, say 14 of 3, right? That's the power that 14 is raised to get 3. So we have rules for exponents, right? And that's the very first lecture we did in this spring of 2020 that was online. And there are properties of logarithms that are very similar to the rules for exponents. So one rule, the product addition rule for logarithms, is log base b of m plus log base b of n. So same base, adding two different logarithms together, you can multiply the things inside. So why does this work? Here's a little bit of a explanation about why this works. I wish this thing focused better, but we just have to live with what we've got. Log identities, b to the log base b of m is m, b to the log base b of n is n, b to the log base b of m times n is m times n. Right, so these are the log identities, the inverse identities that we had. So if you put that together, m times n, right, is this, but m times n is also this times that. If we have the same base, we can add the exponents together. So b raised to this is equal to that, and so that means the two things in the exponents have to be the same. So lots of letters, a little bit confusing, but how do we illustrate with 2 times 3 equals 6? Hopefully everybody's happy with the idea that 2 times 3 equals 6. We can do this in terms of logarithms by saying, well, 2 is, whatever base you want. 2 is equal to whatever base you want raised to the log base b of 2. Right? And 3 is b raised to whatever base you want to the log base b of 3. That's what these numbers are. This is the power that base is raised to get 2 out. This is the power that this base is raised to get 3. And 6 is b raised to the log base b of 6. So 2 times 3 equals 6. What is that? Well, 2 is this. And the 3 is that. And 6 is this. But two things multiplied together with the same base means add the exponents. I'm running out of space. I'd love to have a whiteboard. There we go. Okay, so what does that mean? That has to be equal to that. And so this whole thing is just saying 2 times 3 equals 6, right? But just writing 2, that's this part, times 3, which is this part, in a complicated way. And powers add, right, when you multiply the two things together. So product addition rule, if you're adding two separate logarithms, multiply the two logarithms, the two things inside the logarithms together, and you can combine it to one logarithm. So we can expand and contract some things. Log base 17 of 34, what's that equal to? Well, 34 I can write as 2 times 17. That becomes log base 17 of 2 plus log base 17 of 17. Right? So if we have two things multiplied together inside, way up here, inside of the logarithm, we can take that and break it apart into 2 added together. So 2 times 17 inside the logarithm can be broken apart into 2 logarithms. And we know that log base 17 of 17 is just 1. So it's actually just, oh my God, where'd it go? There it is, log base 17 of 2 plus 1. Log base 3 of 7 plus log base 3 of 4. Same base, so that means we can contract it. becomes one logarithm, and we get what's inside the number inside the logarithm by multiplying the 7 times the 4. So we get log base 328. So 2 logarithms added together can be combined. One logarithm that's got a product inside the logarithm can be split into 2. Same thing for quotient subtraction rules. Pretty much exactly the same argument. M over n, well, m can be written as something raised to a power. N can be written as something raised to a power. The fraction itself can be written as the base raised to a power. So the base raised to a power is m over n, which is b log b over m over b log b to the n, which is that. But when you have the same base and you're dividing, you subtract the powers. So 6 over 3 equals 2. We know that 6, whatever number you want, log base b of 6 is the power you raise the base to get 6. Same thing with 3. Log base b of 3. And same thing with 2. So 6 over 3 equals 2. That becomes b to the log base b of 6, because that's my 6, over b to the log base b of 3, because that's my 3, and that should be b to the log base b of 2. But these two things, same base, division, that means you subtract. So if you subtract the powers, right, you get that logarithm. So log base b of 6 minus log base b of 3, that's the same thing as log base b of 6 divided by 3, which is 2. So we can expand and contract logarithms with this rule, and let me write it down again so that we know what that is. There's our logarithms. So if we have a fraction set of logarithm, we can expand it into 2 separate logarithms using a subtraction. So log base 5 of 2 over 3 becomes log base 5 of 2 minus log base 5 of the denominator. If we have 2 separate logarithms, we can pull them together into one logarithm. Log base 7 of 5 minus log base 7 of 18 will become log base 7 of 5 divided by 18. So the minus sign means that goes to the bottom, that goes to the top. Okay, so that's our division rules. And then finally we have, we have the power coefficient rule. Log base b to the m to the r is r log base bm. The power can come out front as the coefficient, or coefficient can go in front as a power. And so this is using the rule that a to the b to the c, if you have exponents stacked up, you just multiply them together. So 2 cubed equals 8. We know that where am I? Right, 8 equals log base, 8 equals the base raised to log base b of 8. And we know that 2 equals log base, 2 equals b to the log base b of 2. So 2 cubed, which is this side, is b to the log base b of 2, quantity cubed. Now I can just multiply this 3 times the exponent and get that. But we also know that 2 cubed is equal to 8. And so this thing is the same thing with this. 8 is 2 cubed. I can take the 3 out front of the logarithm and rewrite log base b of 8 as 3 log base b of 2, because these two things have to be equal. So log base 2 of 25, We know that 25 is 5 squared. We can take the 2 and put it out front as a power. So we get 2 times log base 2 of 5. 2 log base 3 of 4. What's that equal to? Well, we know we can take the 2 as a coefficient, so we can put it in as a power. And so we get log base 3 of 4 squared, which is 16. So that's 3 powers. Last one is the change of base property, which we don't use quite so much as we've done in the past, because computers can now do, most computers can do logarithms to any base. But if you want to know log base b of m, you can find it using base 10 logarithms or base e logarithms. And most calculators will have a log button, that's my base 10 logarithm button, and an ln button, that's my base e logarithm button. So if we want to convert from base b to base 10, keep in mind that m can be b log b to the m. M is also 10 to the log base m. B is 10 to the log base b. So m equals b log b to the log base b of m, but b is also 10 to the log base b. So you plug everything in. M, the number that you're looking for, you can write it as 10 to the log of m, but you can also write the base in terms of powers of 10 and then the log base b of m. So how does that actually work for this? Log base 7 of 12. We saw a while ago when we were introducing these, we had log base 7 of 12 and we didn't know exactly how to calculate this. So log base 7 of 12, my number 12, I can write that in 2 different ways. I can write that as 10 raised to the log of 12 using my identities. But then I can also write 7 as being 10 to the log of 7. Great. So, and I can also write 12 as being 7 raised to the log base 7 of 12. So there's a whole bunch of different numbers. So combining these two, I get 12 equals, now take this expression and plug it in here for 7. 10 to the log 7, quantity raised to the log base 7 of 12. And I can rewrite that as 10, multiply these two things together, log base 7, log of 7, this is base 10, right? Times log 7 of 12. But what's 12 equal to? 10 to the log base 10 to the log base 10 of 12. So what's the upshot? This thing has to be equal to those two. Great. My calculator can calculate this and that, so that means I can calculate this. So log base 5 of 20, how can you actually calculate that? Well, take log base 10 of 20 and divide it by log base 10 of take log base 10 of the number and divide it by log base 10 of the base. So 20, if I take logarithm base 10, that's 1.301. If I take 5, logarithm base 5 of that, that's 0.699 roughly. So 1.301 divided by 0.699, about 1.861. You might get a different number because I'm rounding, and rounding errors can affect things. So what about base E? Log base 5 of 20 equals, well, you don't have to do base 10 if you don't want. You could do it base E. Remember that ln means log base E. So ln of 20 over ln of 5. 20 ln log base E is 2.995. well, 2.996. And if we take 5, if I take ln of that, I get 1.609. So log of 20 divided by log of 5 is 2.996 divided by 1.609. And if we do that division, we get 1.862. These numbers should actually be the same, but I rounded in different places, so the numbers are slightly different. But it doesn't matter what base you use. So if you've got a calculator like mine that only has ln, base e, and log, which is base 10, you can still figure out any of the logarithms. So we're back in example 19. Jane had $400 invested at 6% annual interest, compounded continuously and monthly. We did solve this. This you can just use the fundamental rule to solve. And then divide both sides by 0.06. You get t equals natural logarithm of 3/2 divided by 0.06, which is about 6.75. So using the fundamental rule, you can convert this into a logarithmic equation. Calculator can calculate that, divide by 0.06, you get about 0.6.75. This one we couldn't do because of the base is 1.05. So if we use the fundamental rule again, what do we get? That's FUND, fundamental rule. We get log base 1.005, because that's my base, of the number, which is 3/2 equals 12t. Divide both sides by 12. I'll just write it as 1/12 times log 1.005 of 3/2 equals t. So there's my answer, but I don't know what this is. But on the other hand, I can calculate that, because that's log base 10 of 3/2 divided by log base 10 of 1.005, and that equals t. And you can calculate that because your calculator can do base 10 logarithms, and it ends up being 6.77. So compounding 12 times a year takes a little bit longer than compounding infinitely often. But this is the change of base theorem. So we have, we'll get to a summary in the next lecture.